Hello, everybody, and welcome to the second day of TWSS 2021. We are so excited that you're here to join us. We've had a very exciting event so far. We have now had people from 17 different countries log in over the course of our event. So we're always happy to see people from all across the world. Today we have in the morning a series of short presentations. The first presentation that we have is Jared Letty. He is a research scientist here, speaking on modeling neutral and charged fluids in VSEM. And Dr. Jared Letty, he's been a research scientist here at TechX for 4 years. And prior to that, he received his PhD from the University of York, specializing in, of course, plasma physics. All right, Jared, I think that's enough. One last thing I wanted to tell people, actually, before I forget, we are going to be recording all of these talks. We hope to get them up to YouTube by next week, once we have them all edited and processed. And then anyone who would like to receive an evaluation of our software can go online and request an evaluation through our website if you get excited with some of the stuff that you see throughout the event. So without that, I'm going to turn it over to Jared.
Thanks, Colleen. I'm Jared Letty. Like she said, I'm a research scientist at TechX. I'm going to turn on my video when I can. But for now, I'll just keep going. So I'm going to talk about modeling neutral and charged fluids in VSEM, which is, well, those of you that are familiar with VSEM, you might know we've had neutral fluid capability in the software for years, but it's been limited in its capacity. It's been effectively static fields that you can use as reactants to generate like ionization products or something like that. So for part of a research project I recently was working on for the Department of Energy, we developed some new fluid models, one of which is where you evolve the fluid via the Euler equations, and the other is a sort of MHD model, but it's hybrid, and it's something we can do nicely because we already have the PIC code. We can treat the ions kinetically still. So this is for problems where maybe you have, the ion dynamics are important to the physics, but the electron dynamics are less important, and so we can treat them as a fluid. Let's see. No. Okay, so for both of these, this now allows us to actually evolve the fluids instead of having them just be some static field in the background of our simulation. And we've also included some more interesting boundary conditions than just slab boundary conditions. So you're able to model these fluids in your CAD geometries or interesting shapes, whatever it is that you want to do. And I'll show some examples of that. And another nice thing is that these fluids are CPU and GPU capable, so you can distribute them across whatever hardware you have. They haven't been released yet. They should be coming out with VSEM 12, and I'll talk more about that as well. So just a little background, what I mean when I say the Euler equations, for those that aren't familiar, this is what we have. This is the system of equations we're evolving. So we have three fields. We have density, we have flux, and we have energy for our fluid. And we evolve them via these equations. And the nice thing about this is that they're all in kind of this conservative form. And so we can end up using a finite volume method nicely and easily for this neutral fluid. And so this is just continuity equation, our momentum equation, and then the energy equation. And we use this relationship, and our closure here is kind of the standard adiabatic closure. The method we use to implement this is, like I said, finite volume. And so what we can do, if this is our simulation grid and say we're looking at the center cell, and we'll call it the ith cell, we're using the standard muscle scheme to calculate the flux at the faces and use those face fluxes to actually evolve the field at the center point. And then these are numerical fluxes. And so we're using the Lax flux scheme where basically the numerical flux at the face is just the average of the physical flux, which is just the quantity times the velocity at the center of the neighboring cell. And so, for example, the numerical flux at this face, this I plus 1/2 face, is the physical flux at the center face averaged with the flux at the face to the right. And then you have this extra term here, which helps with stability, which is basically the maximum flux. So this is the scheme we used. And so I'm going to just show you a little bit in vSim itself. And so let me stop my share and then start it again. So this is an example that we'll include in vSim 12 with these capabilities. This is a Kelvin-Helmholtz instability. And for those that are not familiar with this, effectively, this is where we have some density of neutral gas, and it peaks in the center and decreases towards the edges. And we're using periodic boundary conditions on all sides here. And then if we look at the flux, this is what kind of gives it, this is what seeds the instability. We have this shear flow. And so we have all the gas is flowing to the right here, but you can see it's flowing faster in the middle, slower on the edges. And in fact, it's flowing in the opposite direction on the edges. And so we have this shear. In addition to that, we also need to seed the instability with a little vertical perturbation. So this is the flux in the y direction. And you can see we're pushing this side down a little bit and this side up a little bit. And this will give us just enough perturbation to seed the instability. And we can see if I go back to the density, as we evolve in time, we get this sort of kink that forms. And then we get the standard kind of Kelvin-Helmholtz instability that shows up. Just to give you an idea, I'm just running this on my local machine. It's 4,000 steps to get this, and it is pretty quick. So that's nice. We can run that whole simulation to get the instability in 15 seconds or so. So we're pleased with the neutral fluid speed, performance, and also its capability. It's getting the instability quite nicely, and it agrees with the theory. But this is all nice. This is a periodic box. If you're doing some very theoretical stuff, maybe that's appropriate. But a lot of people are going to have real geometries, and so we made sure that we implemented this in so that you can have cut cells cut by whatever geometry shapes you want. And so I'll show a quick example of that as well. Let me share it. So this is a shock simulation, and again, it's kind of a standard problem for benchmarking neutral fluid models. But the nice thing about this is that the simulation domain is a square, but I flipped it so that we have actually a diamond simulation domain. And what we have is effectively a shock where it's high density and pressure at the top, low density and pressure at the bottom. And so we expect a wave to propagate down and then behave accordingly as it reflects off of the edges of our box. And so we can see that is, in fact, what happens. We get this nice symmetry that doesn't break throughout the simulation of these waves bouncing around our box. And so this we've benchmarked against the other codes that do the same type of problem and find that we agree quite well in time. And importantly, one of the most important things is that we don't lose the symmetry in the simulation. It means we're treating the boundaries correctly. So that is where we are with the neutral fluid model. And as I mentioned before, we expect that to come out in the next major release. So for those of you interested in modeling neutral fluids alongside the other capabilities of vSim, you will be able to do that. So that's the neutral fluid. I want to talk a little bit about the hybrid fluid model, and this is a bit more challenging than the neutral fluid model. Neutral fluid models have been around for a long time. These hybrid fluid models, in theory, have been around for a long time, but in practice, people are still releasing research papers, modifying algorithms, and things like that. And so, like I said before, sometimes the electron timescales and behavior are not important to the physics that you have in your problem, but the ion kinetics are. And we particularly maybe care about the ion kinetics because they're non-Maxwellian, or they have large tails, things like that. And so in these cases, we want to have kinetic or pick ions. We'd like to be able to skip over those fluid timescales, like the electron timescales. By treating the electrons as a fluid, we're able to increase the time step, decrease the spatial resolution requirements because Debye is less important. But we are making an assumption. And so we have to be careful about which problems we can apply this to. Again, some equations, but this is just to give you an idea. We're treating the ions as kinetic. So this is just literally the kinetic equation for the ions. We're using electric and magnetic fields. The important stuff, the stuff that makes this different, I suppose, is the electron fluid. And so we only have one equation for our electrons, which is we're solving for the pressure, the electron pressure here. And this is a fairly standard pressure equation. We have viscous heating and the heat flux, and everything else is pretty normal. But importantly, this is an electrostatic type model. And so we calculate the electric field from Ohm's law. And so we can use the information we know about the ions. So this like VI we're getting from the kinetic ions themselves, along with the J, the grad P. And then we do have a magnetic field, but we're calculating it from the electric field we get from Ohm's law. So this is the system we're solving, and this is from the Stanier paper in 2018, the Journal of Computational Physics. So it's not something, the model itself isn't something we developed, we just implemented it. And one thing you'll notice, so if we have kinetic ions, but then we use something like the ion velocity in an equation to calculate the electric field on a grid, that means we're having to take moments of this kinetic distribution. And so we are able to take our ion kinetic information, which is just a bunch of particles at random locations, at non-grid point locations, and we take averages of those and deposit them onto the grid so that we can use these field quantities like VI and J and the density as well, are all taken from these moments of the kinetic equation. So we implemented this, and then we wanted to benchmark it to make sure we're getting correct answers, because that is important. And so we expect that this hybrid model should, in some cases anyway, some physics problems, give as good an answer as pick, but with increased speed. And in some cases, we also expect that a full fluid approximation would be incorrect. And so we're kind of sitting in that middle ground where we're trading performance for accuracy, but not accuracy because we're putting it to the right problems where we don't care about those electron dynamics as much. And so some of those problems are this ion acoustic Landau damping. Because the Landau damping is done on the ion timescales, and because of the kinetic ion effects, this is a good choice for applying this algorithm. Likewise, the gem challenge problem, which is a reconnection problem, is also appropriate. So I'm going to go through these two examples and just show you some of our results so you can see that our implementation is accurate. So just a review of what Landau damping is, our setup anyway for this problem. We have a thermal plasma, and it has a density perturbation at the ion acoustic wavelength. And this results in an electrostatic ion acoustic wave. So we add this perturbation at the right wavelength, and we expect it to oscillate. But because of kinetic ion effects, this oscillation will be damped, and the oscillation will shrink as the ions effectively take energy from the wave and from the electrons. And this damping rate and oscillation frequency are known from theory for this type of problem, which is why it's a good benchmarking problem. So I can show you these plots, but I'll also pull up VSEM. This is the electric field in the center of our problem. Actually, well, let me pull up VSEM first, because I think it would be useful to see the initial setup. So let's go here. So we're setting up a perturbation that is roughly the wavelength of our box, which also we've designed to be the ion acoustic wavelength. And so what we'd expect is that this perturbation oscillates in time. And we can see that is what happens. And the wavelength stays constant. It's just we get this oscillation. But you'll notice the oscillation is indeed shrinking, and that's what we expect and what we want, because what we want to do is measure the rate at which that is damping. And so we added a history to look at the electric field at the center point, and here's our oscillation. It's nice and even. It's at a particular frequency, and you can see it is damping. And so I can take the log of that, and well, that is not great. Let's put this min at like -6. You can see we have this nice exponential damping rate, linear in log space, which is what we expect. And that's the plot I was showing on my slides as well. So let me pull those back up and show you in more detail some of the results. So we have, again, this is that same plot, the damping, it's happening at a particular frequency. We can FFT this to get the frequency, and then we can fit that history that I showed you. So there's the history. You can see that same oscillation that's damped, and we fit that, and we know the theoretical damping rate, and we can see our damping rate, and we're within 15%. And so that's not bad. And we can also do things to improve this. So Landau damping simulations are notoriously noisy. And so one thing you can do to increase the fidelity of such a simulation is increase particles per cell, increase resolution, that sort of thing. And so there are ways we can refine this simulation. But I think it shows, one, that we're capturing the physics that we should be, and two, that we're doing it to a fair degree of accuracy. And this is particularly for some TE over TI is 5, which tells us that we're saving quite a bit of computational speed by not having to resolve the electron timescales. The electron timescales, if the energies or temperatures were equal, would still be, we'd be saving roughly 40 times with speed in being able to just resolve the ion cyclotron time instead of the electron cyclotron time. At TE over TI is 5, we're getting roughly 5 times that, and so we're getting a significant savings by going to this hybrid method. So that's the Landau damping. I want to talk a little bit about this GEM challenge as well. This is, like I said, a reconnection problem. And so the setup here is that we have a current sheet. You can see we have an electron pressure and density that peaks in the center, and this all has some velocity into the page. And what that means is that above this sheet, we have some positive magnetic field that's being generated by this current density. And below the sheet, we have a constant negative electric field. So pointing to the left, below, right, above. And this is actually a stable configuration if we have an ideal plasma. But plasmas are not ideal. They have resistivity and other kinetic effects. And we expect that this will become unstable in those cases. And it will become unstable. And what we should get is effectively some BY, some vertical magnetic field that starts to form, and we'll get islands that develop in this type of situation, some magnetic islands. And so we do indeed see that happen. And so this is BY, this is the vertical magnetic field. And we would expect, well, this starts off exactly zero. But over time, we get this BY that starts to develop due to these kinetic effects and resistive effects. And that's what's giving us our islands then. If we have that BX and we have now a BY, we'll get some sort of shape of magnetic field that is, a magnetic island in nature. So we'll get that reconnection that starts. And we can measure this integrated flux. So this is the flux in the Y direction, integrated across the X domain. And then we can see that at time zero, we have no magnetic flux in the Y direction. But as the reconnection starts to occur, we get this significant increase. And we can look at other papers that do this kinetically. And we could even model it kinetically in VSIM. And we see this same rise in the same time. I will say that we ran this with 20 particles per cell. And to give you some context, for the Landau damping, we ran 50,000 particles per cell because Landau damping is quite noisy. It turns out this is also a little noisy. And so after the reconnection starts to happen, we reach a point where the noise is too much. And so the magnetic flux starts to fall where really we would expect it to remain roughly constant. And so this is, again, something that we could expect to increase particles per cell and see this fidelity maintained further and further. There are also things you can do with having very quiet initial condition starts for your particle positions and things like that, because we're doing all this averaging, this moment taking to get electron density, or sorry, ion density and ion velocity. There's some intrinsic noise in these types of simulations. And one thing we do to remove that is we smooth the fields. And this is, again, something that they do in the paper. And I can show you real quick the Jim challenge. So here is VSIM. You can see we have all these fields in the hybrid model. We have magnetic field, we have current density electric field, we have the resistiveless electric field, current density, ion current density. We also have this smooth versus the non-smooth. And you can see perhaps the difference it makes to smooth versus not smoothing. And this is kind of necessary to get the noise to average over the noise a bit, and is, if done correctly, should not affect the accuracy of the results. And so, again, you can see all this in that Stanier paper if you're interested. They also do the smoothing. So let me share my slides again. I am nearing the end here. So in summary, we have VSIM 12 that's going to be coming out with the ability to evolve fluids, and this is something new to VSIM. And these fluids can be both neutral and charged. I will say the charged it's a specific model, right? It's this hybrid model. It's not just generic charged fluids, but it has a specific application that we find useful. If you want to do full fluids, full charge plasma fluids, then we do have a product for that as well, USIM. So the fluids can be evolved in periodics, slab geometry with slab boundaries, or even more complicated geometries. Just a note, in case you noticed, I didn't show you much of the actual setup, but everything I showed in VSIM today was in tech setup, but it will be in the GUI for VSIM 12. So never fear. And that's all. So if you have any questions, I will be happy to answer them. Thanks for listening.
Well, very good. Jared. It's always neat to see what's coming down the pike, right? If anyone has questions, there is a Q&A box at the bottom of the screen, and you can type them in there and we will read them and be able to answer them. Well, Jared will, not me. As I said before, this talk will be recorded and put up on YouTube. So hopefully by sometime next week, so that you can refer back to it if there was anything else that you wanted to see a second time. And if you are interested at all in evaluating VSIM 11, if you haven't tried the newest version, if you go to the TechX website at txcorp.com, txcorp.com, you can request a 30-day evaluation of the latest version of any of our software. So, and it looks like we have a couple of questions to start out with, Jared. So the first question is, can the electron fluid be given a drift velocity?
So we initialize the electron fluid with just the pressure, because that's the only field we have for the electrons. The electrons we assume to be calculated, the electron velocity we assume to be J minus VI or NVI. And so you could set up an initial current density field and give the ions an initial velocity, and the difference between those will give the electrons some effective initial velocity as well. So if that's what you're looking for, then yes, we can do that. Where is that term? Oh, if so, where's that term? Yeah. So I can go back to those equations, but I didn't show a couple of things like J is NVI plus NVE. And so that allows you to do that calculation that I just mentioned. But so like this VE here in the PE equation, that is calculated from J minus NVI. So yes, I think you can give the electron some initial drift velocity relative to the ions, but it's not as simple as just, specifying VE.
Okay.
And then Ming-Che, did you ever compare fluid or hybrid model with pure PIC? So we did do so for the Landau, we did. So there's a couple of things. Yes, we did for some established PIC results, and they agreed. So if I show you, for example, the Landau damping, they agree very well. The GEM model, they agree up to a point, and then we lose some fidelity, whereas the PIC would have stayed up high after this. And we did also try and do Landau damping in VSIM, so our own PIC results to compare with the Landau damping. It's just very expensive. Doing Landau damping kinetically, especially of an ion acoustic wave, is very expensive, and also quite noisy. You need to use many tens of thousands particles per cell, and we ran it and saw agreements up to maybe the third peak here, and then the PIC just flattened out and got noisy, whereas the hybrid stays quite nice for much longer. So yes, we did do the comparison, and we see good agreement, especially with the Landau damping and up to a point with the GEM. The other question, VSIM 12 be released. I can't give a firm date on that, but it's our next version, and we have some good features for it that we expect to be out, either the end of this year or early into next year is the plan. So we'll see how that goes. So Udo asks, can these initial conditions for the electrons be exported from a fully kinetic pre-run? So yes, for sure they could be. If the question is if it's automated and something that you could just like have VSIM do, as of now, no, but maybe that's something we could look into actually implementing, because that could be interesting to be able to do that kinetic initial run and then switch to hybrid fairly seamlessly. But right now, no, you'd have to do like some analyzers to get that data, and then you could import them as like pi funcs and that sort of thing into the fields that you want.
So there's another question that talks about how will this work with particles? I don't know if you've.
So the hybrid model uses particles. It uses kinetic particles. I guess I can show you real quick the simulation for GEM. So you'll notice I have all these fields, which are rough. These are kind of fluid fields. But I do have particle data up here as well. And so we can look at the ions specifically and see how they evolve. So this is so it starts off nice and clean as you'd expect from a kinetic simulation. And then the particles start to move around and we see the pressure, the density diffuse and also obtain some sort of perturbations. And so the hybrid model does use it does use kinetics. If you're talking about the neutral fluid model, the way it would interact with kinetics would be through the reactions framework. And so you could have, if you had like a neutral fluid background and say you had some kinetic species that were also, you expect the kinetics of those species to be important, then you could have them in the same domain. And then you would just need to specify reactions between them, whether it's elastic or ionization or whatever it is, that would allow the fluids to interact with the kinetic species.
That answers the next question, which was how will the neutral fluids work with particles?
Good.
Great. And it looks like another question. So how many particles per cell do you need to run with for the hybrid model?
It depends on the problem. Like I said, for the Landau damping one, we ran with 50,000 particles per cell. And so it was a lot, but that's because Landau damping is quite a noisy problem. The GEM problem, we ran with 20 particles per cell, and maybe we should have run with more, but I don't think we need to go as high as the Landau damping problem, right? So there's not necessarily a strict and fast rule for how many you need, but because we're taking these ions and taking the moments to get the density and things like that, the more particles you have, the less noisy that'll be. So you can see, for example, here is the kinetics. This is the weights that I'm plotting, and so higher weights are localized here. We would expect to see this same type of shape if I go and look at the ion charge density, right? So I can click that and we'll see, let me turn off those. You can see that same distribution is showing up, but it is somewhat noisy. And that is because we are using 20 particles per cell instead of maybe 50 or 100. And so it's always a bit of a not a game, but you have to just play around with it and see how smooth can you get it without with balancing the performance and the computational cost. And I think that's the same with, I mean, that's kind of the game you play with all simulations. What resolution do you need in order to get accurate results, but without detrimentally affecting your computational performance? So it's the same type of thing here. Daniel Holland says, can the initial ion distribution be loaded from file? And this is specifically for the hybrid model, I assume. And so, yes, it definitely can be. I guess it depends on what type of file we're talking about. You could load it from a vsim file, no problem. If you had some theoretical functional form for your distribution, you could also do that. I think if you're getting your ion distribution from, I don't know, another piece of software, you'd have to figure out a way to either like fit it and use that fit function to load the distribution into vsim or something else. But yeah, that's I think that are all the different ways you could do that. Ming Che, will the fluid models work correctly for particle collisions with a moving fluid? Yes, that is the hope. I mean, they should do, because all the reactions are local, right? The way we do the reactions is by looking at the the fluid in a cell, or the reactants basically in a single cell. And so in this case, it'd be a fluid reactant with a kinetic species, perhaps. And so the way we then do that is to sample the fluid distribution to get some sort of pseudo particle that has the right velocities based on the fluid velocity distribution, the right weight based on the density, and we interact that with the particle, and then we feed that back into the fluid and the particle. And so if the fluid had some initial velocity, like some flow rates to a particular direction, then we would expect that momentum to be imparted to the kinetic species as well. Yes.
Gosh, we've had some great questions today. Very cool. So if anyone, we've got Jared for a few more minutes, if you have any last questions you want to ask before we take a break until our next presentation. Thank you so much. This is always, like I said, it's always fun to see, the development pipeline and what else we're going to be offering as well. So, okay, I think we'll go ahead and stop there. Thank you so very much, Jared. That was, thank you for taking the time to do this. Our next presentation will come up in about an hour. So we will have at that time, Luke Adams is going to be presenting a presentation on grid instability growth rates of electrostatic particle and cell simulation algorithms. Oh, we did get one more question, which asked about, will that feature be available in VSIM PD?
So the Euler fluid, I think we're going to put in VSIM base, and the hybrid model will be in PD. That is my understanding, but we haven't officially decided on that. So, but that's I'm pretty sure the way we're going to go with it. Yeah.
Okay. Great. All right. Well, thank you, Jared. Thanks everyone else who has joined us so far. We will see you in about an hour.